Hello everyone, welcome back to the course. In this lecture, I'm doing something innovative. I'm not showing my writing by screen sharing, but I'm using a real webcam, which is my phone, to record the screen. In this way, I can better point to the quantities or to some terms to better show the math. Hopefully it will work well. So in the last lecture, we talked about the equivalence between the mean square error and maximum likelihood estimation. So for linear regression model. So the mean square error, we define the loss as this one, the square difference, okay, of your prediction and your true target, and then you take the average. And the maximum likelihood estimation says, I assume my model, my data is indeed generated by some linear transformation of your data plus some noise, okay? And here I call it omega, where omega is true, it's the true weights, but they are unknown to humans, okay? We don't know what is the weights, but it's already there, it's some constant. And epsilon is actually independent noise, Gaussian noise, generated from this distribution, okay? So basically the mean of the epsilon is 0 and it has some variance, okay? So I'm assuming my data is indeed given by a linear transformation or affine transformation in the original feature space. And then for each data, I give you some noise, okay? The mean, the error, the Gaussian noise. And then you may get this T for some time, and for some other data, you may get that T, okay? So this is my assumption. Then the W, okay, is the argmax of my data, okay, of my data parameterized by my W, okay. So this is my W, okay. This is my hat, okay. Estimates the MLE estimate is I choose such W that makes my data as likely as possible. And we show that they are actually equivalent. And we know the solution, we have a closed form solution to that, which is W hat. Okay, it's sometimes called ordinary least square, which is X transpose X inverse X transpose T. Okay, so this is what we have learned in the last lecture. And in traditional statistics, we typically analyze the bias or the variance of the of some estimate. And we're going to show that such estimate is unbiased. So we can call it a theorem or a claim. Assume T is indeed generated by some transformation, omega transpose X plus epsilon, where epsilon, omega again, it's true but unknown, the unknown weights that you're going to estimate, okay? And epsilon is zero-centered independent noise, okay? It doesn't have to be Gaussian because in our derivation, we will not use the property of Gaussian, but it must be zero mean, okay? I just say have some noise, maybe larger or maybe smaller, okay? And for different X, you may have different epsilon. It doesn't have to be identically distributed, but it must be independent. For different data samples, the epsilon will not be correlated to each other, okay? Then WOSL, which is this term, is an unbiased estimate of omega, okay? Omega is my true weights. Okay. So by saying unbiased, I'm just saying the expectation over my OLS is indeed omega, okay? This is the definition or this meaning by saying it's an unbiased estimate. But when we talk about expectation, we must be clear what is the random variables and what are the distributions. If we don't have that, then the meaning of the expectation is unclear, okay? It's syntax error, you have some component missing. So here the random variable, of course, I have epsilon, it's my random variable, okay? But you can also think of x is a random variable. So you can say, I have a distribution over my data x, okay? So x is generated by its own distribution. And for any x, okay, I know the expected target, which is W omega transpose x. But it's contaminated by some noise, epsilon. So I can say epsilon is generated by P of epsilon given x, okay? For a particular x, I have some distribution over epsilon. It may be something like this, okay? This is epsilon. Or maybe it's something like this, okay? But eventually the mean must be 0, okay? So maybe it goes down sharper here, okay? But the mean is 0, okay? This is the requirement. The mean of the epsilon is 0. Okay, but you can also say I treat x is a constant, okay? So I don't want to model the distribution of x. I only say I can generate different targets based on different noise, and I do it again and again. It's this equation also holds. Okay. So proof. Okay. It's not difficult to show that the expectation is just omega. The only thing you need to do is you plug in what is that, and then you compute the expectation. Okay. So I say I just plug in the ordinary least square solution, which is x transpose x inverse x transpose t, okay? T is just omega transpose x plus epsilon, but here it gives you one single t, but now I need a bold t, which is a vector. So we need the vector, matrix vector notation, which is x omega plus epsilon, okay? And we know the expectation is a linear process. So expectation of AF plus DG, suppose f is a function of x, okay? X over P of x. Then it gives me A of expectation of f plus B of expectation of g, okay? So now this gives me expectation over x transpose x inverse x transpose x omega plus expectation over x transpose x inverse x transpose x, no, x transpose omega, epsilon, sorry. Okay, so I'm just distributing this term, to every term here. So where's the random variables? The random variable is still x and epsilon. Okay, I just omit that distribution, x epsilon. Okay, I can write it like P of dx. Okay. Then for this term, it's obvious that you don't have epsilon, right? This term does not have epsilon. So I say this is a function of my random variable, but now it's a constant function, then the expectation is just a constant. So I can just ignore omega. And regardless of what x is, we assume it's invertible, okay? So it's invertible. So this gives you the identity matrix. So regardless of what it gives you, I will have omega, right? So it's say the expectation of x and epsilon of omega. Then the omega does not contain x and epsilon, right? Omega is not a function of x and epsilon. Omega is some constant, so it just gives you omega. And for this term, x and epsilon may not be independent, but given any x, okay, I have a conditional distribution of epsilon, so I can write things in a clearer way. So I can say this is x, okay, then epsilon x transpose x inverse x transpose epsilon, right? Then, we consider what is I given x. So I have x, okay, x transpose x inverse x transpose. Then the expectation of my epsilon, epsilon generated by P of epsilon given x, okay. And I know for any x, the expectation over epsilon is 0. Okay, for any x, no matter what x you have, the noise is always centered at 0. So it gives you 0. Then this entire term gives you 0. Okay. So here, x and epsilon may not be independent. Okay, for some x, I had a picture there. For some x, maybe the noise is small. For some x, the noise is large. But I'm saying for any x, the epsilon is centered at 0. So I can put my expectation immediate before my epsilon given that x. Okay, then I take the expectation over x. It's just 0. Okay, it's 0, so it's omega. Okay, done. So it basically says if I take expectation over my data where my x can generate from its input distribution, and then I have some output noise, and then if I do the ordinary least square, it will be an unbiased estimate because I take the expectation. It's exactly the same as my unknown constant omega. So you can also omit x, okay? I say my x here now is not a random variable. I only have that many x, but my target can be generated by noise and the equation still holds, right? So here, whether you have the distribution over x doesn't change too much. So variance, this is given by a theorem called Gauss-Markov theorem. Okay, so the ordinary least square estimate is the best linear unbiased estimate. Okay, so it just says, for linear estimate, it means that my omega has to have some form of a linear transformation of your target. Okay, this is the definition of a linear estimate. And then unbiased just means the expectation when you have this is unbiased. And then the best, it says the variance is the lowest, okay, the lowest variance. Okay, and the proof of this is omitted in the lecture. You can check the reference. It's not too difficult. It's just replacing the expectation into the variance of something. So interpretation. Okay. So the interpretation here is not saying, I have infinite many samples in my training data, and if I fit the model, then it gives me an unbiased estimate or an asymptotically unbiased estimate. This is another thing. This is not what this theorem says. Okay, this theorem says even if I have very few samples, maybe 5, okay, maybe 6, but I must have it invertible. Okay, so even if I have a few samples, finite number of samples, if I can repeatedly generate that many 5 samples or that many finite samples, suppose my data set is 100, okay, for any number, as long as I make the matrix invertible, okay, then I can repeatedly generate different 100 samples, okay. I have these 100 samples, I have another 100 samples. For each of my data sets, okay, I estimate a W. For another data set, I estimate another W. If I have infinite number of data sets and I average all these Ws, it gives me an unbiased estimate. It's the same as the true weights omega here. Okay, this is the interpretation. So the random variable, okay, is data, okay, including input, okay, but more important, it's output, okay, output, or the noise, right? So the output is subject to some linear transformation of input plus some noise, okay? So you can have the expectation over input as well if you have a distribution of x. If you don't have that, you just fix the input. If you have the noise, it's the same. So it says data, the random variable is my data, which is either the input or maybe input is optional, but the output is repeatedly drawn from data distribution. Okay. And you have for each data. So I say my data can be repeatedly drawn from the data distribution. So for a specific data set, I estimate, or maybe I call it data set 1, or maybe data set I estimate a W I, okay, this is not my iteration, but this I is of different data sets. It's not the sample of data sets, but it's different data sets. I do different experiments. Then I would say the average over, maybe I have I samples in total, then I have this. Okay, it's the omega. So this is my interpretation. So my random variable is the data set, okay? I repeatedly draw different data sets according to the data distribution. And for each data set, you estimate a weight. And if you do it for infinite many times, your expectation or the average of the weights is the same as your true weights. Okay. And if you do this, the variance of such estimate is the minimal. Okay. So this is some traditional statistical analysis. We analyze the bias, the variance, so on and so forth. But the main concern is main concern is my data is not generated by a linear model or an affine model, okay? Right? So it's a very typical frequentist analysis. We assume that my data samples are generated by some distribution, and if you assume that is correct, what can you analyze, okay? But unfortunately, this may not be correct, okay? This may not be correct, right? So, you know, in artificial intelligence, usually we're dealing with highly complicated tasks. If this is correct, then our world is super simple and we don't even have to have artificial intelligence. The artificial intelligence problems will be well solved. But in real applications, there are very few cases that you can have the linear transformation, like the stock price. I don't think it's linear, right? Or maybe you estimate maybe the weight of some animal based on some genotype or based on some measure of features. It's not linear either. And you know, you do image classification or text classification, it could not be linear, right? Even if you do image generation, they are not linear. Nothing is linear. So the assumption is not true. If the assumption is not true, then the analysis is not very helpful. So the assumption, if this assumption is not true, then the analysis here is not very helpful. The analysis here just says, if my model is linear, I have this result, but I don't have that model, so the result is not very helpful here. So why not we assume, okay, given a data sample X, okay, the true target T is a function of X plus some noise epsilon, where epsilon is noise, okay, and it's zero-centered noise, zero mean noise. Okay, so this is a reasonable assumption because, you know, I don't have to say my data is linear. So maybe my data is highly unlinear. And if I try, for example, X at this point, okay, if I try many times, maybe I get different targets, okay? I get different targets. And I can take the expectation of the target, the expectation of T, where T is sampled from P of T given X, okay? Then I can call this function, define it as f of X, okay? And then anything else, you know, any randomness involved is modeled by epsilon, okay? And this time, if you have this, then of course the epsilon is zero-centered, right? Because you know, you can take the expectation over T minus f of T, f of X, right? t is sampled from pt given x. And then this term becomes a constant, and you just take the expectation over xt. But this is f of x, then it gives you 0. Okay. So here we assume that given the data sample x, the true target is a function plus some noise, where the noise is 0 mean and also is independent. Now this time, this gives me a very mild assumption. We basically have no assumption. We basically say there's some uncertainty that you cannot model based on x. Okay, for example, I would like to estimate the weight of an animal, and I know the size, I know the kind of the animal. The weight of an animal itself can vary unless you know it. So there's some effects that cannot be modeled from X, or there's some true randomness. For example, quantum mechanics, okay? You cannot predict the future because there are some true randomness. And the only thing we require is data sample size are independent, okay? And the 0 mean I mentioned here, that it's not a requirement either, because you can always define f of x to make epsilon 0 mean. Now we consider the expected error. Okay, and so I would take my expectation over my error, which is my prediction h of x, minus my target, okay, t or t of x, okay. So we should be careful. What is the expectation? The expectation here is my data x is generated by some distribution, and then for an x, okay, I generate t by having f of x. It's a constant, it's not a random variable, plus some noise epsilon, which is a random variable. So epsilon is generated by p of epsilon given x. So I can concisely write it as x epsilon, okay? And we consider the error, which is the mean square error. So this is the mean square error, okay? So the question is this error the training error, the training objective, or the error of unseen data? Okay, it actually reflects the error of unseen data, right? Because I'm saying my x is generated by its own distribution. So this is my x base, this is my x, okay? And for the training, you are using a subset, and actually it's a very small subset, like even 1 million samples is a very small subset among all possible input, right? But now I'm saying I consider the expected error when x is generated from its own distribution. Then it's very likely that you don't get your training samples. And if it's real number, then it's almost impossible to get the training samples. So it actually reflects the error of unseen data. So this is actually the measure of success of a machine learning model, okay? We don't care about the training error. If you optimize the training error to 0, it doesn't help too much. But we care about how much you would make an error for unseen data, which is sampled from its generic distribution, not from your training data. So I would claim this is actually expectation of, so I can plug in fx plus epsilon as t, right? Because I say the t, the target, is indeed a transformation of x. It's a deterministic transformation of x, except that you have some noise, okay? Right? So I even omit x and epsilon, self-clear. So I say h of x squared plus f of x squared. Okay, no, I would expand it in a clever way. I say hx, so I consider them as a single term. Right? Then, expectation is linear process, so I can distribute expectation into each of the term. And this term, you know, you don't have epsilon here. And this term is actually x epsilon h of x minus f of x. Okay. Did I have a 2? Yes. Plus. Okay. But this term does not have x, so I only consider epsilon. And now we observe this term is 0, right? Because, you know, for whatever x you have, then I can compute the expectation of epsilon first. Then it gives you 0. Then you compute the expectation of x, it still gives you 0. So this term just vanishes. It's just 0. So now I can rearrange terms and say, what is my expectation that my prediction differs from my 2 targets? Plus, what is the variance of your noise? Okay, so if you have more noise, then of course my prediction is worse. But even if you don't have noise, maybe your hypothesis, your learned hypothesis is different from your true function, the true function, which is f of x, okay, f of x. Maybe this is your h of x. Maybe you still have a difference, then this is your error. So now I decompose this term. This is sometimes known as the risk, okay, risk of h. So this is the expected loss or expected error. So for generic samples from its own distribution, how much error you would make. Okay, so this is one important result. And this is sometimes known as the irreducible error because you cannot model the noise. Suppose I predict the weight of an animal and I know the size of the animal. Can I deterministically determine the weight of an animal? No, because there's noise. So this term, maybe you don't have enough information, or maybe the words just happens in a stochastic way. It cannot be reduced, no matter what machine learning model you choose. And for this term, it can be further decomposed into a few terms. And then we'll show that it's a trade-off between what is the power of your functions and what is the variance of your functions. Okay. So now I'm decomposing this term. The first term, x. Okay. And I will say h is a hypothesis, okay, mapping from some input space to output space learned by a training data set D, okay? So I call it h of D, okay? So I just make my training sets more explicit. Okay? Then I will say this term is the same as minus expectation over my data samples h prime of x, okay, plus samples h prime of x minus f of x. Okay, it looks scary, but let's first verify what does it mean by this equation. This equation introduces one term, minus some term, plus some term, then it cancels out, nothing happens, okay? But I'm introducing a term of what is my average hypothesis, okay? My average hypothesis for predicting this sample if I'm repeatedly generating different data. So I still have a distribution over data and I repeatedly generate my data, then I repeatedly learn different hypothesis functions. And what if I average this hypothesis function? This is my term here, okay? So I subtract one term and I add one term, so nothing changed. So this gives me this term, okay, plus. So you see there's a square. So I group them as two terms. This is A term, this is B term, okay? Plus 2 times, okay, AB. So now I'm going to take the expectation over D again, okay? Because if you are given one particular D, then you are saying, okay, I'm working with this data set, but maybe this data set is peculiar. And I'm hoping to analyze the average performance if you are repeatedly generate different data samples D, okay? So I take the expectation over different Ds. Okay, then this gives me, so the expectation of D and X, you can also write it as two expectations, okay? So it doesn't matter. So HD X minus HD prime square, okay? The square is in the expectation. Plus, do I have X here? Yes. Do I have D here? No. So I just say expectation over X. And then expectation over D prime, HD prime over X minus F of X. Plus 2 times expectation over D and X, okay? But if I have the expectation over D, then this gives me expectation over HD X. This is the expectation over D prime, HD prime X. But they are the same thing. I just rename D as D prime, so this term is 0, right? So I can say expectation over X, expectation over D, okay? HD X minus HD prime over X, right? Because, you know, I take the expectation over D, then the only term here is this term that contains D. And then I can, all other terms are linear. So I can just take the expectation over D immediately before this term. Then it gives me the quantity of expectation over D, HD, but this is the expectation of D prime, HD prime, they're the same thing. So this term gives me 0. So the entire term just vanishes, okay? This term just vanishes, 0. So now I can delete this term, it's 0. Okay. So now this gives me a very good interpretation of my error, okay, of my expected error. Suppose my data is repeatedly sampled from its data distribution, then consider an unseen data sample. So suppose my data is repeatedly generated by a data distribution, then for some unseen sample, my error or my measure of success is computed in this way, and then it's decomposed into two terms, okay, plus a noise, okay? So it's decomposed into 3 terms, 1, 2, 3, plus a noise. So it's actually, this term is actually the bias term or the bias square, okay? This is the, sorry. This term is actually the variance term. And this term is actually the bias term, but it's the bias square, okay? So you see why it's called variance. A variance of maybe a random variable is the expectation of the random variable minus the expectation of the random variable, then square, right? So it's just this, right? I first compute the average here, and how a particular output differs from my average, and I take the square and take the expectation, it's just the variance, right? And why this is known as the bias term? The bias term says for on average data samples, okay? So I repeatedly generate my data samples and I compute my hypothesis based on all the samples and I make an average. Okay, did I miss the square? Okay, did I miss this bracket? Yes. So the expectation is here, okay? So it basically says, even if you repeatedly generate your data samples and you compute the average of your prediction, it's imperfect. It's not my F, okay? So this is the bias term. So the bias term, the bias is defined as your estimate, maybe your estimate minus the true parameter, right? So you remember it's before, if the model is indeed linear, then I have no bias. It's an unbiased estimate. But now this time it says it's not linear. So the true model is f of x. Then, it's a bias square, okay? So this gives me a bias variance decomposition. Okay. The expected error or the expected reducible error is decomposed. So the variance is basically what you learn for a particular dataset D differs what you learn for repeatedly learning the hypothesis and taking average. So this is the variance. And the bias is what you can learn by repeatedly drawing the data set, and I consider the average prediction minus the true prediction. So this is the variance bias decomposition. Example. Assume my t is generated by some polynomial, okay? a1x, or maybe a0 plus x1, a1, x plus a2, x2 plus until a n xn for some unknown n, okay? So I assume my model is indeed generated by this, except some noise, okay? It's zero-centered noise. Then what if my hypothesis class, for example, is a low-order polynomial, okay? So my hypothesis class is h of x is some w0 plus a1 x plus a2 x2 so on and so forth until a d x d, okay? Plus the prediction has no epsilon. Okay, assume, so now what if d is less than or equal to n, or d is small? Okay, I say d is small. For example, suppose my true order is 3, okay, and I model it by a linear curve, okay, a linear line, okay. Then suppose my true model is a function like this, okay, this is my true function. Then what if I have a few data samples like this, okay, I have a data, for the first data set I generate, I have a function like this. Then I learn my hypothesis class like this, okay. Then for my second data sample like this, right, I learn a function like this, okay. And for my third data set, okay, generated like this, I have a function like this, okay. So in general, the average of my hypothesis is maybe the red curve. So this is my average. So this curve is the average of my hypothesis class, okay? And I know the true curve is this. The true curve, I just drew this curve, right? And the difference between this square, the square difference between the red line and the brown curve is the bias square, okay? And the red line between the variance of the colored lines is the variance, okay? So now you see if D small, you have a high bias, because no matter how you learn, you cannot learn this. You cannot reduce this gap, okay? It has low variance, right? Because you know, all the curves here look all the same. So it has low variance, but it has high bias. So if D is large, okay, so I still have these data sets, okay? I don't know if I can plot. Okay, good, very good. So, okay. So suppose my D, for example, is 5, okay? I can have 5 order polynomial. Then for the black dots, I probably learn some curve like this, okay? Okay. But for the blue curve, I probably learn a curve like this. Is it possible? Yes. And for the green curve, I probably learn a 5th order polynomial as this, okay? Where's my green? Oh, it's okay. Okay, so these are my learned 5th order polynomial fitting into the true 3 order polynomial, okay? So suppose it's true. Then on average, if you generate the data samples many times, you have you can repeatedly generate your data sample. Then on average, what you learn will be a true function. Okay, will be this function. And what is the, so this function is the expectation of my data set. Okay, and what do you have as f of x is also this function, because I know the linear model is unbiased. I know the ordinary least square is unbiased, and you know, if you consider the feature of x squared, x cubic, so on and so forth, you know, it's still a linear regression, but in the polynomial feature space, it's unbiased. And then eventually, when you take the expectation, it will be the same as that. But for each individual data set, you know, for this data set, okay, you may learn something ridiculous, like it goes up very high at this point. It doesn't make sense, but it shows that it's of high variance, but it's of low bias. And you know, in this case, if your hypothesis class contains your true function, is contained in your hypothesis class, and with an unbiased estimate, for example, ordinary least square, then you know the expectation of this will be exactly the same as your true function. But this is only a necessary condition for being unbiased, because you have to also measure what is your estimate. But these two pictures just shows that what is my what does it mean by the variance and the bias, okay? So the variance is if you repeatedly generate different data samples, how a particular hypothesis differs from its average, okay? This is the variance. How the average hypothesis differs from the true function, this is the bias, okay? And you know, if this is large, then it's of high bias and low high variance and low bias. Okay. So you know, your hypothesis class is small, then you typically have this. Then if your hypothesis class is large, then you typically have that. Okay. And you know, intuitively you can plot it like the power of your hypothesis, okay? And the variance or the bias. So usually if your hypothesis is too powerful, then the variance will be increasing, okay? But your bias will be decreasing, okay? And at some point you don't have bias if you use a good estimate. So this is the variance, and this is the bias. Now the sweet point is here, okay? Or maybe somewhere here, okay? So you would like to seek a trade-off that maintains a low bias as well as a low variance in a reasonable sense, okay? So this is the bias variance trade-off. Okay, just to summarize a little bit, we have decomposed my expected error, okay? Suppose my data set is repeated drawn, my expected error over unseen data samples, okay, over the data samples from its true distribution of my prediction minus the target, and we use the mean square error, which is the bias square plus the variance plus the noise, okay? So this what you need to remember, okay? The noise is the variance of the noise, okay? And this is not too difficult to remember, right? It's the bias variance trade-off with some irreducible noise. And with this term, with this term in mind, now I can remember the below term. So I don't remember the following term. I will derive the following term based on this intuition. So the bias is how much you would learn on average differs from your true target. Differs from your true target, which is f of x. Okay, and I don't have epsilon here. The variance is how much you would learn for one data set, differs how much you would learn based on the average hypothesis. So this is, okay, what you would learn based on one data set minus how much you would learn based on the average of your hypothesis. Okay. Plus the variance of the noise. So the noise is your epsilon, the epsilon square. Okay, it's zero mean, but the variance exists, and then it's irreducible. It has nothing to do with your hypothesis. Okay, that's it for today. Thanks for watching. See you next time.